Okay, so in order to reduce the time for attendance check, I will just call your name in 5 minutes ahead. So, of course, you can join the course at 9 o'clock, but there are some students, about 7 students already in the classroom or in this live stream. So I'll just call your name. So if you are here, please leave your name in the chatting log, then I can check your name. 심준호 씨 안녕하세요. 네, 홍주표 씨 안녕하세요. 네, 배민열 씨 안녕하세요. 이충화 씨 안녕하세요. 이승빈 씨 안녕하세요. 이재혁 씨 안녕하세요. 고하늘 씨 안녕하세요. 김유신 씨 안녕하세요. 김민선 씨 안녕하세요. 조대현 씨 안녕하세요. 서하연 씨 안녕하세요. 네, 이윤지 씨 안녕하세요. 네, 장수범 씨 안녕하세요. Okay, so this is 9 o'clock. Okay, so I will call the remaining names. 이정태 씨, 자, 정상아 씨, 정민서 씨, 이정태 씨 안녕하세요. 정상아 씨, 정민서 씨, 배서령 씨, 이경배 씨, 이정태 씨, 네네, 이정태 씨, 네, 알겠습니다. 배서령 씨, 이경배 씨, 최승규 씨, Mr. Victor Kujak. So yes, I can see your name. 네, 김성수 씨, 네, 알겠습니다. Okay, let me give you the final call. 정상아 씨, 정민서 씨, 배서령 씨, 이경배 씨, 최승규 씨. Okay. So if you are late, then please let me know. Later I will check. 네, 정민서 씨 안녕하세요. 네. Okay, then please leave your message. Then I will check your late attendance. Okay. So have you all submitted the homework number 1? Actually, I checked the homework number 1, and there are 3 students who have not submitted the homework number 1. I think that homework number 1 is not that difficult, but the reason why I gave you that problem was just to let you know how to use the GES system, or check whether everything goes smooth with your lecture. Some of those students who have not submitted their homework dropped the course, so I don't care about them any further. However, there is also one student who are still in this classroom but have not submitted the homework. So I'm afraid that actually that can happen again and again. But please note that the weighting factor for our total evaluation will be 30% for entire homework if everything goes quite smooth. I mean that if midterm examination and final examination will occur, in this case 30%, 30%, and 30% ratio. And as I told you before in the last lecture, so in an unfortunate case where midterm examination is not available in offline fashion, so in this case the weighting factor for homework and final examination will be increased. So homework is not just an exercise, but that is really important for your evaluation. So I strongly recommend you to be more careful about submitting your homework answers. Okay. So if you have any questions, please let me know. And for example, if you have some difficulties to perform the homework number 1, then please let me know. I can help you in various senses. So please let me know. And if you have any questions related with our lecture, then please let me know. So you are always allowed or encouraged to give me questions. Then I will try to my best to answer your question. Okay. So no question from the student side. So anybody? Okay. So then I will just start our today's lecture. So maybe you are curious why I do not provide the PowerPoint file. So PowerPoint file, in this case, PowerPoint file is already available to you. So please have a look at our repository like 2 years ago or 3 years ago. I think that even 4 more times can be available to you if you are willing to. Then you can find them in these repositories. So PowerPoint file will not be explicitly given to you. So just to try to find them all. Okay. And by the way, today's lecture is related with again a review of circuit theory and some related stuffs to study this entire semester. Okay, so if you have any questions, please let me know. I can always slow down my lecture progress, then repeat the explanation again and again. Okay, since there is no question from student side, I will just continue our previous discussion. So if you remember, then we have introduced a definition of a circuit. Circuit is defined as a set of connected circuit elements. So maybe you remember it. So previously in previous lecture we have discussed about what is a circuit element, what is the most significant feature of circuit elements. In this case, we first define something called terminals. Okay, there can be multiple number of terminals. For example, there can be 2 terminals, 3 terminals, 4 terminals, or even larger number of terminals is allowed. And we, for example, generally we say that there is n terminal in our circuit element. So that is one thing we have to keep in mind. Okay, so for example, we can think about 2 terminal circuit elements which has 2 terminals, and also we can think about 3 terminal circuit elements. Okay, it has 3 different terminals and each of them can be connected to certain position. Okay, also we can think about 4 terminal circuit element. It has 1, 2, 3 and 4, and it can be connected to certain point. Okay, so do you have any question about my description about n-terminal circuit element? That is not that difficult to understand this concept, n-terminal circuit element and their connection. So if we just list all of circuit elements, 1 circuit element, 2 circuit elements, and their connectivity, then it is enough for us to describe the circuit completely. Okay, and another important information about our circuit elements is it has n terminals, and for each terminal, so for example, here we have the first terminal and here we have the second terminal, then each of these terminal has its own quantities, terminal quantities. What was it? So what are they? They were current, terminal current, and terminal voltage. Yes, once again, here we have terminal current and terminal voltage. You know it. So let's just consider n-terminal device instead of a two-terminal device. For example, think about a three-terminal circuit element. So sometimes I say device, but should be regarded as the equivalent word for circuit elements. So there is a number one terminal and number two terminal and number three terminal. Then my question is, how many terminal quantities are required to fully specify these three terminal circuit elements? Then you can think that this is I, V. Also this one need I and V, and also we need I and V. So the total number of terminal quantities to describe this circuit element will be the number of terminals times 2. So we should have 6 different quantities to fully describe this one. So are you guys all with me? Then let me just give you a simple question. So please answer my question, everybody. If you are here, then let's think about n-terminal circuit element. Yes, this one has n-terminal, and n can be 2, 3, 4, or something. So say that starting from number 1, number 2, there are many, and ends up with its nth terminal. Then my question is, how many terminal elements are required to specify this n-terminal circuit elements? So please leave your answer in the chatting log, then I can see your understanding. So please don't be shy, then everybody. So please. Okay, thank you. Yes, thank you. You all understand my point quite well. Okay, so now you understand each n-terminal circuit element should have 2 times its number of terminals n. So if we have 4-terminal device, then we have to specify 8 terminal quantities. 4 of them are terminal currents and 4 of them are terminal voltage. Okay, so it is quite good, and thank you for your participation. And let's now visit to our simplest circuit from now on. Okay. And it is much better for me to draw a large one. Okay, then I will just clear them all. Then I wanted to say here we have the element number 1. Let's say this is number 1, and here we have element number 2. Then it is the number 1 is a 2-terminal circuit element, and number 2 is also happen to be a 2-terminal device, and happen to be we connect terminal 1 of element 1 and terminal 1 of element 2 are connected to each other, and also we wanted to connect in this way. So do you have any question about this connection? So although that is quite simple, but you can easily understand this is a complete circuit and you have seen it before. For example, one realization of this simplest circuit topology is, let's say V1 is, for example, this is voltage source. And say this is a resistor. Then what will happen? In this case, you will have current, and the Ohm's law will be applied. But the purpose of our today's review is not just to hand calculate this simplest circuit, but give you a systematic way to analyze this system. Once you can analyze this simplest system, then you can easily expand your technique to more elaborated and complicated system. So you understand my purpose. So for a while, just think that this number 1 and number 2 are generic circuit elements. So it can be, for example, inductor, capacitor, voltage source, anything can be this circuit element 1 and 2. Okay, so I wanted to remind you that once again, even in this discussion, you can ask me questions, so then I can hold my discussion and try to answer your question. Okay, so up to now, everything will be quite easy. And let's say that this is circuit number terminal number 1 and terminal number 2. Terminal number 1 and terminal number 2. Of course, later you will find different names for these terminals. For example, we will think about this case. We can think about different terminals for a certain 3-terminal circuit element. Then how can you name those terminals? Of course, we can say that this is a first, this is a second, or this is a third. But if we love certain circuit elements, then instead of naming them as just how can I say, number, we try to name those terminals certain alphabetic number. For example, we will later say this is a source and this is a gate, and later we will call it as drain. So this is kind of a nickname for those terminals, but this is just a naming convention. And in this case, in order to make it everything quite general, I will just name them with numbers. But say that this is numbers. For example, I can call it as H terminal and this is L terminal. Fine. So just name is not that important. Then if you have a question, please let me know anytime. Then I can try to answer your question. So now you understand we need 4 terminal quantities and also 4 terminal quantities. Now all of you understand this topic. So why don't you just explicitly introduce those quantities? You know 4 for circuit number 1 and another 4 for circuit number 2. So this one should have two terminal currents, and it should be written as I and V. So why don't you write down in this way? This superscript is used for circuit element 1, and my subscript 1 is used for what? The terminal index. Okay, so this alphabet itself is used to whether this is a terminal current or terminal voltage, and superscript is to represent the index for circuit element, and subscript is used to its terminal index. Okay, then it is straightforward that we have to have 1, 2, and V 1, 2. Wow. And here we have I, and this is second element, and it's first. So second element and it's first. Okay. Also we have a second element and second terminal, and voltage of second element and second terminal. So I have introduced just a new convention for our terminal variables. So this is not very universal. So if you read different textbook, then you will find many different ways to represent the same quantity. But in this lecture, for why, I will just use this convention. So if you don't understand this convention, then please let me know. Okay. Then now we can find that in order to specify this total 8 unknown terminal quantities, we need some equations. So how many equations are required in this case? We have 8 unknown variables. In order to fully specify these 8 unknown variables, then usually we need to have 8 independent equations. So that is quite common. So are you with me about the necessary? We need 8 equations. Then since this one, the first circuit contribute to 4 terminal quantities, so it is quite natural that this one should provide us 4 equations. And this one should provide us 4 equations. Okay, each of them provide 4 unknowns, so each of them should provide the same number of equations to specify them. So that is quite reasonable. So let me just list those 4 equations required for fully specifying these 4 unknown variables. 오케이, 배세령 씨 나중에 지각 체크를 하도록 하겠습니다. Okay, so now we need to list 4 equations for each terminal. Okay, 1, 2, 3, and 4. Yes, also we can think about 4 unknown equations, 4 equations for them. So you remember that actually we have discussed about this one a little bit in previous lecture 1. Then let me just repeat it again. One thing we have to keep in mind is current conservation. So when you say current conservation in this case, it simply means that the total sum of terminal current should vanish. So why don't you just write down the current conservation in a equation form? In this case, I wanted to say that I11, so the first terminal current, and I12, its second terminal current, their sum should vanish. So are you with me? And if we go to this one, this second circuit element, then it is true that the sum of second element and its first terminal current and second terminal current should vanish. So we can find this current conservation rule in first element and second element. Okay, so if you have a question, please let me know. So I just introduce one equation and it has the relation between two terminal currents, and still we have three unknown equations, and for a while just leave the second one and list third and fourth one. Third and fourth one, no, so the appearance order is not that important, but third and fourth one is voltage specification and also voltage specification. Oh, so we have connection of each terminal, and each terminal says that I am connected to different terminal. So my voltage and that terminal's voltage should be identical, because you know here we have a line, and this is a line, and physically this line is made of a perfect conductor, so no voltage difference is allowed between this point and that point. Okay, so voltage should be the same for I think that something is wrong with my pencil. Okay. Oh, sorry about that. Oh, okay. Sorry about this interruption. So something happens to my pencil. Sorry about that, and I will try to erase it. Okay, it works perfect once again. Let's come back. So our previous discussion just before interruption was, since our two terminals are connected through a perfect conductor, so no voltage difference can occur between them. So now we can say, so let me just write down here as a third equation. And for example, first element and first terminal, that is connected to second element first terminal. So here we have second element and first terminal. Good. And how about the second terminal of our element? Then in this case, the first element and second terminal is also connected to the second element, its second terminal. Okay, now we have two additional equations. Good. So everybody understand this situation? Wow. Then natural question is, natural step is, okay, we have applied this step to our circuit number 1, then why don't you just apply our same procedure to our circuit number 2? Then could you please write down, in this case, the first terminal of our second element is connected to what? The first element of our first element, first terminal. Also, we have to have, yes, we have to have this relation. Okay, now we have it. Okay. Okay. Then now I have a question. It is something wrong. There is something wrong. Certainly that is not that good for our analysis. Could you please, everybody, could you please write down your opinion about something wrong in this analysis? Okay. So what I have done is just to introduce current conservation. So current conservation just is this relation, sum of two terminal currents should vanish, and sum of two terminal currents should vanish. That's one thing. And we have applied voltage connectivity. So first terminal and first terminal are connected, and second terminal are connected. Once again, first terminal are connected, and second terminal are connected. So now we have already 6 equations, and wow, here we have one missing equation, and since we have here one missing equation, then we will have full 8 equations. But I wanted to stress that this is wrong. Something is wrong in this procedure. I just introduced a long procedure. So what is your opinion about badness about this procedure? Do you have any idea? So you can freely show your opinion. Okay, still you are a little bit shy. So then I can just give the answer. My answer is, please have a look at, for example, please have a look at this one and this one, or please have a look at this one and this one. What happens? You know that this equation is originated from our circuit element 1, and this one is originated from our circuit element 2. But how do they look like? They are really identical. because the connection is mutual. Therefore, if this one is connected to that one and that one is connected to this one, then when we just consider connectivity, then each of them will give you the same equation. So I am connected to them, that is connected to me. So no further information cannot happen through this connectivity. Okay, so are you with me? I mean that simply specifying the connectivity cannot give you the full number of equations required for our analysis. That is my point. So we need additional equation because we have still missing information. So that is the thing I wanted to say. How can we solve this difficulty? That is remedied by this way. Now we introduce a midpoint, and of course we can introduce another midpoint, and usually this midpoint where terminals are meeting each other is called a node, and a node. Then this node has its own property, like what? Voltage. And let's say that voltage. This is node voltage. So let's say that this is node voltage, and say this is node 1 and node 2. Then by introducing these node voltages, the total number of unknown variables has been increased from 8. 8 means that 4 for circuit element 1 and 4 for circuit element 2. But now we have 2 further additional circuit node voltage. So let me just write down in this way. 4 from 1 plus 4 from number 2, finally 2 from circuit node. Okay, so now the number of unknown variables are increased, so we have to specify now 10 different equations. Then how can we specify these 10 different equations? But life becomes much easier when we introduce a node. Then please write down once again the equation. The equation is still given by the first terminal voltage should be equal to first node voltage. Then for this second element, we have to have the first node voltage is also equal to first node voltage. So up to now, everything is just identical with our previous bad situation. There's no further information because the V1 of node is just that can be just cancelled out, and we can easily introduce a certain information like terminal voltages are the same for their first terminals. So in this case, this is not that good. Only one information is available from these two equations. But point is, now we have introduced this node voltage as another unknown variable. So now we can impose another equation. Then what will be the another equation for this case? This case, usually, although you sometimes forget about it, but you know, this node is connected to what? Connected to a ground. Ground means that the global reference, voltage reference of your entire circuit. So anything connected to the ground should have zero voltage. So from this connectivity to the ground, we can find the additional equation, and it should written as like V1N is what should be 0. Oh. Why do we have such kind of thing? It is because our node means that here, this node is connected to ground. That gives you an additional relation. Then let's go to our second node. In this case, how can we solve this problem? Of course, if this is connected to the another ground, then everything will be quite easy. But you know, in this case, there is nothing. We are not interested in such kind of trivial system. So usually this node voltage is not known to us, and we have to solve the node voltage. Then what is the rule for specifying this node voltage? That is my main message in today's lecture. Today's lecture, I wanted to say the main rule we have to impose is once again the current conservation. So when we apply the current conservation to a node, it has its own specific name. You know it. If you have attended the circuit theory, then you have heard about it. What is the name for this rule? If we apply the current conservation into a certain position, certain node inside the circuit, then we will call it as simply Kirchhoff's current law. KCL, and it means that the sum of incoming current should vanish. So then why don't you just introduce KCL in this case? If we have to write down the current conservation rule, the KCL, for this second node, then we have to identify what is the current, incoming current from the left side, and what is the current coming from right side. Then you can easily understand that here we have I2 over our first circuit element. Also here we have I2 over our second element. So the direction of this terminal current is always incoming into each circuit element. So if we are talking about the current component like this way, then it is clear that minus this one. This one is corresponding to this guy. And also minus I2 over 2 is corresponding to this guy. And the sum of these two quantities should vanish. Yes, and this is nothing but the KCL applied to the second node, node 2. Okay, then let me just summarize our discussion up to now. We have the simplest circuit system. Here we have one two-terminal circuit element, and here we have another two-terminal circuit element, and they are connected to each other. In this case, the total number of unknown variables to fully specify this system is not just 8, 4 from circuit number 1, but 4 from circuit number 2. In addition to these 8 terminal quantities, also we have to consider 2 further from circuit nodes. And 4 equations should be provided from our circuit element 1 and 4 from circuit element 2. And finally, most importantly, we have to specify 2 additional equations for our circuit node. And now we have studied 2 ways. One way was if that is connected to the ground, then it is quite easy. Node voltage is directly specified, and that's it. So that is quite easy. But otherwise, if our node is not connected to ground, then we have to apply Kirchhoff current law. That is the general way to describe this simple circuit element. Okay, so I wanted to ask you whether all of you understand my discussion up to now. So please don't be shy and leave the message whether you completely understand this concept, or if you have some questions, please leave your message. So if you have completely understand, then say that I have no question any further. And if you have questions, then please give your question to me. So this is for every student. So everybody, please respond to my question or my request. Okay. Thank you. Thank you. Okay, good. So, but I wanted to ask you, all of you, there are 20 students in this live streaming. So, okay, good. Okay, good question. What is the role of ground exactly? So, ground here, that is really a good question. So, physical realization of ground is really a ground. So if you build a circuit, then eventually your circuit should be connected to some larger amount of voltage reference. So that's the reason why ground is called as a ground. So you have build a certain system, then just to finally you have to have the connection between your circuit and certain much wider or larger system. So, however, if we restrict our discussion or our scope only for circuit analysis, then the law of ground is simply says that set your voltage as global zero. In this global zero, then there is no fluctuation at all. Everything is just perfect. So perfectly zero to in its voltage. So uh, so if I come back to your original question, then what is the law of ground exactly? So exactly in our circuit analysis, when something is connected to the ground, then its voltage should be zero. That is one thing from the viewpoint of our circuit analysis, and physically it is really kind of ground. So if you build a system, I mean that build a building and try to connect a certain electricity, provide some certain electricity into your building, then somewhere nearby the building you have to introduce the ground. So ground is typically made of a certain bunch of metal stuff, and you just pound it into real ground. Then the electricity of your entire building is connected to that metal ball, and that metal ball is really attached to the ground, so voltage does not show any further fluctuation. Okay, that is law of ground, voltage ground in reality. But when you consider circuit analysis, that is regarded as just voltage reference. Okay, so everybody give it that you have understood the concept, and thank you for your good question, Kim Min-sun. Okay, then it is really general. So although I know that this procedure is quite tedious, actually you can solve it much easier way. Then why don't you just write down? Then may I erase it? Then let's do it again. I mean that now we consider a specific example of our simplest circuit. Okay, wow, yes, and say that this is the magnitude of our voltage source, and this is the resistance of our resistor. Then usually what we are asked is to calculate current. What is current? Then what you do quite quickly is that from this inspection you really understand that node voltage here is given by V amp, and by applying the Ohm's law you immediately write down in this way: I is given by V amp divided by R. I guess that this is a usual procedure you solve this problem when you have a problem at your hand. Okay, I so I guess everybody will proceed in this way. But what I wanted to say is, how can you recognize that this one is VM? How did you understand this one? Is it because this is connected to ground? So first of all, you say that this is ground, 0 volt. So you have applied the node equation. This node is connected to the ground. You have implicitly used that relation. And second one is from this voltage source, by adding this amplitude or magnitude of this voltage source, you find that the node voltage is given by this one. And how can you obtain this relation? This one is really a property of your voltage source. So why don't you just follow the line like this? Following this line, can you find that this node voltage is equal to V amp? You cannot find it. So this is kind of a property of your voltage source. So what I wanted to say is, although you can quickly solve your problem if this is so simple, but internally in your mind you are implicitly doing certain quick calculation to make your analysis as simple as possible. So let me just do the same thing with a much more complicated way. Okay, then I will try to list 10 equations from now on. So why don't you just follow my convention. For example, here and here we have, I 1 2 and I 1 1, and I wanted to say that sum of I1 I2 equal to 0. Yes, and here we have 2 2. Yes, I will just write down current conservation. Second element and first, second element and second should be 0. I'm just showing that sum of terminal current should vanish. Also, I will apply voltage relations. For example, so first terminal is connected to first node. Second terminal is connected to second node, and first terminal is connected to, oh sorry about that, yes, and second terminal is connected to second node. We have already 8 different equations, and we need two more from one from our voltage source and one from our resistor. We will visit it soon after, and we need two more equations from node characteristics. And node characteristics, we can say that node voltage of our first node, since it is connected to ground, that should be 0. This is the property of our ground, and minus 2 equal to 0. And this is nothing but, this is KCL, Kirchhoff's current law, applied to the second node. Okay, so although we still have unknown equations for voltage source and resistor, but this is really a full set of 10 equations for 10 unknown variables. So do you have any question about my list? I have listed a long list, 10 equations, and they are, in most cases, they are just trivial. For example, sum of current should be 0, or this voltage is equal to that voltage. But anyway, I just generally list them all. If you have questions, please let me know. Then now it's time to specify this yellow boxed one. So up to now, we have not used any special property of voltage source, any special property of resistor. Those 8 equations are quite general. Even when we have a resistor combination, or voltage source capacitor, voltage source resistor, current source inductor, everything will be the same for these 8 equations. Then now we have to specify element specific equations. 2 equations are now required. For example, what is the specific equation for our voltage source, and what is specific equation for our resistor? Do you have any idea? In voltage source, what we have to do is the voltage difference across their 2 terminals should be V amp. So for first element, the voltage difference between second terminal and its first terminal should be given as V amp. Okay, so this is voltage source specification. If this is not the voltage source, we cannot specify such a kind of relation. However, since this is a voltage source always enforces that the voltage difference between its 2 terminals should be a constant or specific quantity specified by voltage source. So in this DC voltage source, we can say the voltage difference between 2 terminals should be V amp, the DC quantity. Do you have any question? Then please let me know. Then let's go to the resistor case. In resistor case, we cannot say this way. 2 should be V amp. No, this is not the property of a resistor. If we have a resistor, then we have to introduce a resistor specific relation. Then what is the relation quite suitable for our resistor? That is, you know that is Ohm's law. So Ohm's law here means that the terminal current of our second terminal should be identical, given by the voltage difference divided by its own characteristic number called resistor. So this is a resistor specific relation, and we call it as Ohm's law. So combining this voltage difference relation and Ohm's law, then when we just insert these 2 equations into it, add into it, then we will have full 10 unambiguous and independent equations. Then you can now solve this 10 by 10 system. So in a matrix form, they can be written as a matrix form. And by solving this matrix equation, then you can get the full information about 8 terminal quantities and 2 node voltages. Of course, these two node voltages will be equal to the terminal voltages, but anyhow, conceptually, you can generalize in this sense. Okay, this is the end of my discussion about this simplest two-terminal circuit elements. Okay, do you have any question? So some students feel that I'm doing the simple job with very complicated means, but point is this is systematic, and yes, systematic, and the procedure which can be easily automated. So without using our intuition, we just specify all related equations, define quantities, and specify the equation related to them. Then we can make a matrix equation. Okay, this is closely related to your homework number 1 and 2, and this is quite important to you, so please give me your response. If you don't have any question, then please say that you have no question, and if you are curious about anything, then please let me know. I can repeat it again and again. So your homework number 1 and 2 are related with this one. Please respond. So Mr. Hanugo, Mr. Go gave me really an interesting question. So KCL, this is the KCL. Yes, and he says that there is a positive sign is missing, and why don't you just write down once again? If we consider just incoming flux, incoming terminal current, then it should be minus I12, and this one should be minus I22. So if I have to write down, then I have to write down in this way: 1, 2 plus minus I2, 2 equal to 0. That is the form when I use consider all kind of a sign. But here, when I write down in this KCL in this part, I just consider this a positive sign and negative sign. So in my opinion, this expression is quite okay and correct. And so how about Mr. Go? How about your opinion? So, or you ask me a different position or different equation? Oh, okay, thank you. But anyway, the question is always welcome, and thank you for your nice try, and thank you for your question, Mr. Go. And yes, good. Please try to ask me question anytime you have any tiny curiosity. Then I will try to. Okay, Mr. Kim. Oh, Yes, Mr. Kim, Mr. Sangsu Kim, it is also really good question. That is actually what I wanted to ask you after all of you understood this one. Oh, thank you for your question. Um, Let me just state his question once again. He said that here I just wrote in this way. The second terminal current of our register. His question is, instead of it, why don't you just use it with, for example, uh, we have two terminals, so we can say, wow, we can write down a relation for this first terminal current. So first terminal current means that the current for this one. Then of course, in this case, what we have to write down is the voltage difference, still voltage difference. However, in this time, we have to say, 1 minus 2 divided by R. You can easily understand this green equation combined with the current conservation rule, this one, we can easily understand this Ohm's law written for the second terminal is identical to the Ohm's law written for our first terminal. So either of them can be used, but I just prefer to use the relation for second terminal, but there is no preference. I mean that there is no inherent preference, but I personally prefer to write down in this way. That is a really good question. However, that is only his first question. He has the second question. If we have multi-terminal devices, so not like two and three terminal devices or four terminal devices, what will happen? That is really good question. So quite naturally, we feel that, okay, this is so simple for two terminal device, but how about n terminal device? If we have three terminal device, then we have to specify what? We have to specify, for example, let's just say that we have terminal 1, 2, 3, then obviously we can have a sum of I1 and I2 and I3 should be 0. That is just current conservation. But still, we need two additional equation for terminal current. So usual way is we specify I2 equal to blah blah blah. Here blah 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 means that a function of terminal quantities, and also I3 should be specified as also terminal quantities. Then these two relations, these two relations is really specific for your circuit element. If your circuit element is MOSFET, for example, certain transistor type, then you will have a certain expression. Also, if your device is a bipolar junction transistor, BJT, which is another three-terminal transistor, then you will have a different specific form. So the lecture progress will give you the specific form for the MOSFET, and possibly, if time allows, for BJT. So that is the main contents of our lecture in this entire semester. So thank you, Mr. Kim, Sangsu Kim. It was really two good questions, and really thank you. Oh, Mr. Kujak, why we have a 10 by 10 matrix is here, that is also really good question. here we have 10 equations. And if we just list them in a matrix type, then we can find a vector of 10 unknown variables. For example, let's do it like this one. I1, I2, V1, V2 over our first circuit elements. And also I can repeat again, I1, I2, V1, V2 over our next circuit element. And also I can add additionally node 1 voltage and node 2 voltage. Then if you write down in a better way, then I can build a 10 by 1 vector. Although this is a 10 by 1 matrix, usually we call it as a vector, or yes, this is called a vector or column vector. And if we just write down our 10 equations for one equation for each row, then we can build 10 by 10 matrix. Then of course here we have a constant B amp, and then we will have also 10 by 1 matrix. So we can have a square matrix, a vector, and this one is unknown, and this one is known, and this one is known. So we can solve this kind of matrix system by multiplying the inverse of our 10 by 10 matrix. So then now you can get the full information about this 10 by 1 vector. Okay, Dr. Kujak, that was a really good question. And another Mr. Kim, Yushin Kim. Oh, no. Yushin Kim, it is also quite a good question, and that can be confused by the newcomers. But you know that V amp and R, I mean that the magnitude of your voltage source and resistance should be regarded as scalar values given by the circuit designer. That is given number. It can be 1 volt, 5 volt, 10,000 volt. That's given, and 1 ohm, 10 kilo ohm, 1 mega ohm, that is given by designers. So you should regard them as a given just constant number, and you have only 10 equations, 10 unknown variables and 10 equations. Okay, that was also a good question. Okay, unfortunately time is up and we should wrap up now. And although I have originally gave you 3 homework problems, but I will reduce it just to number 2. So please solve homework number 1 and 2. And if you have any question related with homework number 1, or I mean that homework number 2, problem 1 and 2, please send me an email, then I will answer your question. And yes, and due is next Monday morning, so please try to solve your homework problem. Thank you. Also, thank you for your active participation, and yes, see you next Monday. Bye. And if you are late, please let me know. Okay, so you are now leave the live streaming. So if you are late, please let me know. And I know that Besaram C came a little late, and I check your attendance, later attendance, and so okay, nobody. Then I will wrap up today's lecture. Bye.